Hello and welcome to another validation of simulation. So, good story with this one. If you've watched some of my other videos, you know that I basically do all, to this point, validation models, and that is things that we are going to do in the software and compare it to some sort of hand calculation. I've talked about it before. If you get a new version of the software, you might want to run a couple tests. Not uncommon for people to make sure that the program is producing results that they expect it to produce. This one, actually, I used not that long ago. A user reached out to me and they said, "Hey, we have some rotating equipment that we want to analyze. How should we approach this? Can we do a dynamic analysis? Can the software rotate this thing at that speed and let us see, what the stresses and displacements are?" And the short answer is yes. Technically, you can, in some cases, take something, apply something like a prescribed rotation to it, bring it up to speed, and see what the outcome is. But it is a rather computationally expensive way to do an analysis. So this person, being a relatively new user, I don't think was aware that in linear static stress you could apply a rotation and see what the results are using the centrifugal load. So that's what I wanted to advise him to do. But I hadn't used that type of loading myself in the software for quite some time. I couldn't remember when the last time was that I used it, so I didn't want to recommend it without having first tested it myself. So this was the problem that I utilized to test this in Autodesk Inventor Nastran. Of course, today we are taking a look at it in Autodesk Fusion 360, which does use Nastran solvers. So we should come out to the same outcome, and we'll find that out here in a minute. But the problem, I took it from Rourke and Young, 6th edition, page 705, section 15.2, case 9. It's a circular disc, conical cross section, rotating about its own axis at 2,500 RPM. Has a 4-inch radius hole at the center. Outer radius is 20 inch. The inner thickness is 1.5 inch, and then it tapers down to a ½ inch in thickness. Steel material properties were utilized, so modulus 36, Poisson's 0.3, density of 0.28, and we will use quarter symmetry so we can help constrain it. We're going to measure the radial and tangential stresses at a distance from the origin, radius of 8.4 inch, and then we should get radial stress and tangential stress somewhere around these values. So let's go ahead and start to build this model up. We'll do a sketch. I'm going to select this face right here. So we'll sketch in the XY plane. And let me change my view cube. And I'm just going to draw a line. We'll start the line, say there, and go there. And then I'm going to draw another line. We'll say from that point to this point. And then we'll just go ahead and dimension those up. So the thickness at the inside is 1.5 inch. And then we can dimension from the origin to the top of that line, and we'll make that 0.75. So half of the line is above the origin, half of the line is below the origin. And then that, remember, is a 4-inch radius hole. Of course, that would end up where the other line is, or did it push the other sketch line over? Take a look at that. I think it put it right on top of the other one. Yes, it did. I can see that line right there. So let's grab that other line, and we'll, whoops, get out of the dimension tool, grab that other line if I can. Grab it by that point. There we go. All right. So then let's start dimensioning the other one. At this end of the model, the thickness is, what did I say, ½ inch, 0.5. And then we'll again dimension from the origin to there. And that dimension would be 0.25. There we go. And then it is out at 20 inches. All right. There we go. All right, and then what I need to do is just draw two more lines going from that endpoint to the endpoint of that line, endpoint there to that point there. Okay, so there we go. 1.5 inch this way, ½ inch this way, 20-inch radius overall, 4-inch radius inner diameter or inner radius hole. What I need to do is sweep this about the origin now. So we'll do a finish sketch. We'll get our revolve command. The profile is already selected. If it wasn't selected, you can just select that profile. The axis we want to rotate it about is the y-axis, and we want to rotate that for 90 degrees. So if the angle is not set to 90, go ahead and do that. And we'll say OK. All right, so there is our 90-degree section of this disk, which is going to rotate about its own axis. Now, we do want to inquire the results at a specific point. So I want to make sure that I have a node at that location. Technically, I don't have to. If I use a fine enough mesh, we should get accurate enough results. Fusion has a really nice point probe, so I could put a probe at the specific XYZ location that I need. What I'm going to do is draw a sketch line at that location, and that location is at r equals 8.4. So let's go ahead and start another sketch on that surface. Again, I'm going to go into the left view, and we'll draw a line, vertical line. Oh, accidentally chose the rectangle command. Let's draw a line. There we go. And we'll dimension that 8.4. There we go. All right, so there we are. There's that. I can finish this sketch. And now I need to go to my modify command, and we will use the split tool, split face tool. And we want to split that face, and the splitting tool I want to use is that sketch line. There we go. Say OK. So there we go. That face is split. So that way, you know, when we generate the mesh, it always places nodes along edges, right? So nodes will always come along these edges. So I'm going to end up with nodes along these edges. And then you absolutely always have nodes anywhere where there is an endpoint, right? So where there's a corner or a vertex in my CAD model, I will end up with a node at that location. So because we split it here, we end up with a vertex right there that will become a node point once we mesh this geometry. Let's go ahead and transfer it over to the simulation workspace and begin with that setup. So in simulation, we're going to do this as a static stress model. Go ahead and create that study. And then let's work our way across the menus. So the material, study material, I'm going to select the material library to be the Fusion 360 material library. And there's a material in here when we set to that. That's just called steel. There it is right there. And if I click on the properties, you can see our density is 0.2836. Young's modulus, yeah, the hand calc bases it off of 30E6. That's pretty close enough, I think, for the accuracy we want. Poisson's ratio is 0.3. Good, let's run with that. We should take a look at what version of the software, by the way. Let me go to the help and about. And I am using version 2.0.12392. I've had the program open a couple times this week to take a look at some different things, and I didn't get any indicator that it needs to download any latest version. So I think that is the latest version. Currently, it is March 26, 2022. So of course, you know, new versions come out relatively frequently, you know, every month to 3 months or so, you might get an update. So just to know what we are, or what version we're working with right now. The constraints, let's go ahead and add our structural constraints. So this is a symmetry face. Let me uncheck the body. We don't want the whole body selected. This is a symmetry face. Looking at my mini axis, the perpendicular direction to that is X. So I'm going to uncheck Y and Z, and we just want to constrain it in X on the face there. Rotating my model around, you can see the mini axis a little better. So Z is perpendicular to this face, so that's what I want to constrain there. So uncheck X and Y, and we'll add our Z constraint there. So here's my X constraints. There's my Z constraint. The only global freedom of translation that I have currently is Y. So I'm going to go ahead and select this edge right there, and we'll give it a Y constraint on that edge just to make sure that we are statically stable. So Y constraint right there, and we'll say OK. So moving over to loads, when we just click on the loads menu, our structural loads, we know that we have forces, pressures, moments, bearing loads, and you can see the list there. I don't need to read it all for you. But if you go to the pull down menu, that's where your other loads are found. And in this case, we want to give it an angular global load. There's a few different ways to apply or define what that angular load is. I'm going to go with the second option here, the axis definition. And we can say that we want a location reference. So I'm going to select this inside surface there, right? And there you can see that it'll then find, what's the center of that based on that curved surface there. And so it picks out a point at x0, y0, z0, so it's going to rotate about the origin. And that's fine. That is exactly what we want, but you could always modify it if you want by typing in appropriate x, y, z locations as well. And then we have a few different ways to define what that load is. We can define it in terms of degrees per second or radians per second, degrees per minute, etc. I've already, done a quick lookup to convert that 2500 RPM to radians per second. And in terms of radians per second, that 2500 RPM becomes 261.8 roughly. And at that point, we can go ahead and say, OK. There we go. All right. I think we're just about ready. The only other thing is the mesh. We'll let it compute the mesh so we can see what we get there. I think it's going to be a pretty coarse mesh, right, at its default. And, keep in mind that this is a 1/2 inch thickness at this end. And let's say that we wanted to get roughly 2 elements through the thickness at its thinnest. So that would tell me that I need a mesh size of about 0.25 inch. So let's go ahead and do that. I'm just going to edit the mesh here, and we'll go with an absolute mesh size. And again, I'm going to make it 0.25. We could probably get away with something a little bit coarser, but I think that's probably a good start. Generate the mesh again. And as soon as that mesh is done, then we are ready to run the analysis. But before we do, remember we split that surface. You can see that we do have nodes right along that edge, and then we have a node right at that location. So that's where we are going to inquire on our values. Okay, let's go ahead and do the solve. One of the great things about Fusion, we could solve it on the cloud if we'd like, or I can solve it locally. I'm going to go ahead and save my cloud credits or tokens, whatever you want to call them, and we will solve it locally. Shouldn't take very long for the solve. You can see it's already prepared, already generated the context. It's not an assembly, so we don't have to worry about that. It's meshed, and it'll go through the computation now. And as soon as that's done, then we can pull back our spreadsheet here and take a look at how the results compare to the hand calculation. As I mentioned, this was somebody that came to me and said, hey, how do we do this type of rotating equipment analysis? And, we want to make sure that we're going to produce the appropriate results, proper results. So this is a good model for doing that. So here we are in the results environment. It is showing me safety factor. We want to take a look at stress results. And you can see what the deformed shape looks like, right? It's just a model, the equivalent of a model spinning at 2500 RPM. So you can see that it's going to grow out radially, and that's in fact what it does. This is an exaggerated or adjusted shape. We could put it on the actual, right, and it's going to be a pretty small displacement. Let's take a look at what that is. Let's take a look at, say, displacement, and we can see out here at the extremity of the model, we're seeing about 2 thousandths of an inch of displacement. So that'd be good to know if it is rotating at some, you know, well, if it's rotating at 2,500 RPM and maybe we have a shield around it, right? What's the amount of clearance that we need between this rotating equipment and the shield? Of course, we want to make it a little bit larger than that, but that gives us some idea of what sort of clearance we need. Let's go ahead and take a look at our stress. And the first result that we want to take a look at is what is our radial stress. So in the radial direction, what is the stress at that location? And that would be, based on my orientation of how I created this model, that would be the z direction or z tensor. So let's go stress normal z. And we want to inquire on that point right there. So I'm going to zoom in a little bit more and we'll go create a surface probe at that location. So okay, and I'm going to drag it off the model a little bit. So yeah, I know I didn't get it quite 100% right on, but close enough. 3962 is what we get for a value. So if I type in that value, that gives us less than 1% difference there. So you can see my computation is the probed value minus the theoretical value divided by the theoretical value multiplied by 100. So we are less than 1% different. I would say that that is good. And then we want to take a look at the tangential stress. So if we look at the x tensor, normal x, that's a value of 7034. We'll plug that into our spreadsheet, 7034, and we're less than 2% different. So both of those, I think, are really nice outcomes, and hopefully you learned something with this example. I think it was kind of a neat example, and glad that I got to show you one, that I actually got to utilize, with a user of the software and say, hey, look, I would go ahead and utilize this centrifugal load because it computes, values that match our hand calcs, and everything looks good there. So thanks for watching. Hope you have a great day. Take care.